Uh, we'll discuss about these dielectric and magnetic materials here. So first of all, we are going to the definitions of the some uh, what is the basic definitions of the dielectric materials. So first of all, what is the dielectric material? Okay, before going to the dielectric material, what is the polarization? What is those? So we have to know. So then only we can define the dielectric. Okay, otherwise without knowing the so this dipole and polarization, dipole moment and polarization, so we don't know what is the dielectric material. So that's why first of all we will discuss about the what is the dipole and what is the dipole moment. Okay, so then we will go for the dielectric. So and we also know about the what is the difference between the insulator and dielectric material also. So we also know that. And and conductor, insulators, dielectric, so that means what is the difference between the conductors and dielectrics also we have to know. So we also discussed that. Okay, first of all we are going here. So this is the what is the electric dipole? What is the definition of electric dipole? In lower classes you studied about the what is the dipole. So basic definition of the dipole is, so two equal and opposite charges are separated by a certain distance. Okay, this arrangement we will call it as electric dipole. So equal and opposite charges are separated by a certain distance. This alignment we will call it as electric dipole. Okay, now electric dipole moment. Electric dipole moment we can denote it as P. Okay, so this what is the charge here? Two charges we are separating. Okay, so charge of the, so these charge carriers, equal and opposite charges we said na. So charge of the these charge carriers into distance between the these two charges is called as so dipole moment. So here we are taking L. Okay, so some cases we are taking 2D. Okay, so at that case we are taking Q into 2D. Otherwise if you will take this distance is L means, so you can take Q into L. Okay, so this is the dipole momentum, dipole moment that equal P bar is equal to Q into L, Q into L. Okay, this is about the electric dipole moment. Okay, units here coulomb meter. Units are the units of electric dipole moment is coulomb meter. Okay, now coming to the polarization. What is the polarization? So polarization means so first of we have to know the, so what is the polarization. For that I am explaining already in while doing the experiment. While doing the experiments, the lab experiment, I will explain you regarding about the, so what is the polarization also I will explain once again here. See here, yeah, so I am taking two capacitor plate, so two plates, so two metallic plates are separated by a certain distance. So these alignment we will call it as a capacitor. So this is the parallel plate capacitor or condenser. Okay, so now so there is this, so if you give some connection charge connect, if you connect to the some battery means what happened here. So charge will be stored inside the capacitor, charge will be stored inside the capacitor. Okay, now so in between the these capacitor plates I am placing one dielectric material, one dielectric material I am placing here. Okay, so the dielectric material or any other material. Okay, any material we are placing. So if you place here dielectric material, now without applying any so charge here, without applying any potential, so what happened, so that dielectric material does not change their alignment anything. So that alignment will be same. See here, so that means if you will take any material, inside there is a nucleus will be there. Around that nucleus electrons will be revolving around that nucleus. Okay, like that, so many electrons will be revolving around that nucleus in different orbits. Okay, so now what happened, so without applying any external field, so what happened, electrons are revolving like this. So similarly at the center nucleus will be there. And what is the charge of the nucleus? So positive, charge of the nucleus is positive. Around that nucleus what happened, electrons are revolving like this. Okay, So now we will apply the electric field here. We will apply the potential difference. If you apply the potential difference, means what happened here? So here we are connecting negative charge here. Here we are connecting positive charge. If you connect the positive charge and negative charge here, so what happened? So inside the material, so many number of atoms will be there. So if you will take any material, so you are taking one material here. So in that material, so many number of atoms. So this is one atom, this is another atom. So like this, so many number of atoms will be present. Okay, so many number of atoms present. Each atom having inside nucleus, around that atom nucleus, electrons will be revolving. Electrons will be revolving like this. Okay, so if you will take each atom, so that each atom like this, it's having like this. Okay, now after applying electric field, so now after applying the potential difference, so we are applying here, so negative charge this side and positive charge this side, and positive charge this side. So now what happened here? So electric field will be produced in between the plates. Electric field will be produced in between the plates. Due to that electric field, what happened? So these so electrons are revolving like this now. So electrons will come one side and nucleus will comes to the another side. That means this atom alignment will become. So now nucleus will be here, electrons will be revolving around the nucleus, but not a circular order. So that means these negative, all negative charge particles are accumulated in this side. So all negative charge, so all electrons will be, so here all electrons will be here in this side. Suppose if you will take here also, all electrons will be this side, only nucleus will move this side, nucleus will move this side. Okay, so that's why what happened? So positive charge is accumulated this side and negative charge is accumulated this side. Okay, so here inside there are so many number of atoms will be there, so many number of atoms will be there. So that's why, so because of that what happened? So all positive charges accumulated this side and all negative charges accumulated this side after applying the electric field or potential difference between these two plates. What happened? Electric field will be developed inside the material. Electric field will be developed inside the material. So due to that electric field, what happened here? All positive charges accumulated this side, all negative charges accumulated this side. Because of the negative charge, so that positive nucleus is attracted towards to the negative plate. So because of the this positive field, so all so electrons having negative charge now, so that all negative charges accumulated, so attracted towards the positive charge. That's why all negative charges accumulated this side. Okay, now what happened here? So this behavior we will call it as polarization. This behavior of material, so like this behavior of material we will call it as polarization. Which materials exhibit the polarization process? Those materials we will call it as dielectric materials. So which materials exhibit the polarization process? So those materials we will call it as dielectric material. So all dielectric materials are insulators. All dielectric materials are insulators. Okay, but all insulators are not dielectrics. All insulators are not dielectrics. Okay, so because some insulating material polarization process does not take place, so that's why those materials are not dielectric materials. Okay, so all dielectric materials are insulators, but all insulators are not dielectric materials, because some insulating materials, what is that, polarization process is not possible. Polarization process is not possible. Those type of materials we will call it, so we does not call as dielectric materials. If polarization process is possible, then only we will call it as dielectric materials. Okay, understood? So now all dielectric materials are the insulating materials. But if you will take conductors, so conductors, why they did not exhibit the, so this polarization process means, so in place of conductors, so already free electrons will be there. So due to that free electrons, what happened? So what is that, current is passing through the circuit. Current is passing through the circuit. That means those free electrons will reaches to the plate, and conduction. What is that? Current is passing through the circuit. So that polarization does not occur in case of conducting materials, because so those what happened? Those electrons and nucleus is not bonded. Okay, so already so many free electrons will be there. So those free electrons touches to the display, connected to the displays, and current is passing through the circuit. So polarization does not occur. That means so these electrons not accumulated here. Electrons not accumulated here. So that electrons reaches to the plate and current is passing through the circuit. Okay, and that's why what happened, that conductors are so by using conductors, so what happened, so making of polarization is not possible. Making of polarization is not possible. That's why so that conducting materials are not dielectric materials. Okay, if polarization is takes place, then only so those materials we will call it as dielectric materials. Dielectric materials. Okay, this is about the dielectric material and polarization also. Now coming to the so definition: separation of charge carriers in the presence of electric field. In the presence of electric field, so that definition we will call it as so polarization. So polarization is nothing but separation of charge carriers in the presence of electric field. In the presence of electric field, this process we will call it as polarization. These type of materials we will call it as dielectric materials. Dielectric materials. Now coming to the so formula for polarization. So here p bar, small p. So this small p. So this small p gives the so uh, what is that? Dielectric moment. So see here, dipole moment. So this dipole moment, small p. So small p is equal to q into l. So small p is called as dipole moment. Okay, otherwise electric dipole moment we will call it as. Okay, now p bar. P bar is the, what is that? P bar here? So polarization is equal to, so polarization p bar, capital P bar is equal to so dipole momentum by volume. So v is here volume. Okay, so now so from this we can say the definition of the polarization. What is the definition of the polarization? Electric dipole momentum per unit volume. Electric dipole moment per unit volume is called as polarization. So once again, so definition of the polarization is already here. Polarization definition is a separation of the charge carriers in the presence of electric field. So that is called as polarization definition. One more definition is so electric dipole momentum per unit volume is called as polarization. Polarization P bar is equal, so capital P here, capital P is equal to small p by V. Okay, so this is here already we know that small p equal to q into L. Already we know that volume. So V is equal to A into L. We will substitute these two values in the above equation. If you substitute in the above equation, here L is the length of the material, Q is the charge. Here A is the area of the material, L is the length of the what is the dipole material. Okay, now so LL gets cancelled. So Q by A. So that P bar is equal to Q by A. Here P bar is the polarization. So polarization is equal to the surface charge density. Polarization is equal to the surface charge density. Already we know that Q by A. Q by A means surface charge density. That means so polarization numerically equals to the surface charge density. P bar is equal to Q by A. Okay. Now, yeah. So no, so here average dipole moment. So that means here capital so capital P is equal to, we will call it as polarization. So that polarization P is equal to, one more definition equal are there. So that is n into mu. So here mu is the average dipole moment. Here P bar is, we will call it as dipole moment now. So if you will take average dipole moment, that equal to mu. Average dipole moment is mu. So polarization P is equal to n into mu. N into mu. Mu is the so average dipole moment. Average dipole moment. What is the n? So number of molecules per unit volume. here n is the number of molecules per unit volume. Okay, so P is equal to n into mu. So here mu is the average dipole moment. P bar is the small p bar. Small p bar is the dipole moment. So mu is the average dipole moment. That is the difference between the small p bar and mu. Okay. Now coming to the, so capital P is the polarization. Polarization, another definition equal to n into mu. So here one more, so already this also one definition, Q by A. So that is the numerically equal to the surface charge density. So one more definition is equal to, so small p bar by V. Okay, so these are the different definitions of the polarization. Now coming to the permittivity. So permittivity, so why we are discussing here permittivity means, so there is some constant will be there, dielectric constant, different dielectric material having different dielectric constant. For explaining the dielectric constant, we have to know the permittivity. What is the permittivity? So permittivity, what is the definition of permittivity? It is denoted by, so epsilon. So that permittivity is denoted by epsilon. So what is the definition of permittivity? Easily polarizable nature of dielectric medium. So already we said that, so dielectric materials are polarized. So dielectric materials are polarized. What is the meaning of polarization? Separation of charge carriers. Separation of charge carriers is called as polarization. So here permittivity. What is the definition of permittivity? Means easily polarizable nature. Easily polarizable nature of dielectric medium. Okay, so that is called as permittivity. So if permittivity is very high means, so that polarization is, so takes place very easily. Polarization will be takes place very easily. Permittivity will be low, so polarization will takes place very hard. That means, so for getting the polarization, we have to apply very huge amount of what voltage or electric field here, electric field. So that's why, so if permittivity is high means that is easily polarizable. Okay, if you will take free space permittivity is 8.85 into 10 to the power of minus 12. That means its value is very low. That permittivity value of free space is very low, 8.85 into 10 to the power of minus 12. So minus 12 means, so before 8 you have to place 8 zeros, 0.00000 up to 12 zeros. After 12 zeros we have to keep the 8. So that means that is a very small value if you will take the free space or vacuum or air. Okay, so that permittivity value is very less. For if you will take dielectric materials, so that is in terms of 10 powers, so 10 power 2, 10 power 3, like that permittivity. So compared to free space, so dielectric material having, so permittivity is very high. So what is the units of permittivity? Permittivity units is coulomb square for Newton meter square. Coulomb square for Newton meter square. How these permittivity units came? So there is a one formula will be there. So two charge carriers are separated by a certain distance. So what happened? There is a force between the two charge carriers. There is a force between the two charge carriers. That force F equal to, so 1 by 4 pi epsilon naught into Q1 Q2 by 1 by 4 pi epsilon naught into Q1 Q2 by R square. Okay, so Q1 Q2 by R square. So based on this formula, so we can write the permittivity units here, 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught into, see here, 1 by 4 pi epsilon naught into Q1 Q2 by R square here. That is the force. So force due to the, so if suppose if two charge carriers are separated by a, so Q1 Q2, these charge carriers are separated by a certain distance. What is the force acting on between means, so F is equal to Q1 Q2 by R square. That is the here constant is 1 by 4 pi epsilon naught. Epsilon naught is the permittivity. So from this formula we can write, so this units. So if you bring this side, so epsilon naught this side, bring F this side, so you can get a coulomb square for Newton meter square. So this is the units for permittivity. Okay, now coming to the, yeah, so so before going to the, so this dielectric polarizability, I will explain the one more definition, dielectric constant. Dielectric constant K. So dielectric constant K is equal to, so C by C naught. C by C naught. What is the C? So already I said that two plates are separated by a certain distance. That means, so that is called as capacitor. Okay, so capacitor, so capacitor, capacitance. So what happens if you place the dielectric material inside the capacitor? Inside the capacitor, that capacitance will be increases. That capacitance will be increases. So that capacitance is increased. Capacitance is depends on the, so that the dielectric constant. So it depends on the dielectric constant. That's why. So if capacitance is increases, so k times. So if you place the dielectric material inside the capacitor, that capacitance will be increased k times. K is the dielectric constant here. K is equal to C by C naught. C by C naught. C is the capacitance of the capacitor. In if so, if you place the dielectric material inside, so C naught is the, so without dielectric material, so capacitance of the capacitor. Okay, so I removed charging button. So after, okay, so now K is C by C naught. So K is equal to C by C naught. So C is the capacitor, capacitance of the so capacitor. When you place the dielectric material, C naught is the capacitance of the capacitor without dielectric material. So ratio of these two is called as dielectric constant. One more is, so K is equal to epsilon by epsilon naught. Epsilon by epsilon naught. Epsilon is the permittivity of the medium. Epsilon naught is the permittivity of the free space. Epsilon naught is the permittivity of the free space. So K is equal to dielectric constant. K is equal to epsilon by epsilon naught. Okay, now so K is the dielectric constant. Epsilon by epsilon naught. Epsilon is the permittivity of the medium. Epsilon naught is the permittivity of the free space. Okay, this is about the one more definition of the dielectric constant. And one more definition. So this is the, here epsilon naught will be there, means so charge carriers are separated by a certain distance in a free space. Okay, suppose F is the same formula, 1 by 4 pi epsilon. Instead of epsilon naught, we writing here. So if charge carriers are separated in a medium, so we will set that F is equal to 1 by 4 pi epsilon naught, epsilon into Q1 Q2 by R square. So now dielectric constant definition. Dielectric constant definition. So dielectric constant. So this what is that? That permittivity is inversely proportional to the force. Inversely proportional to the force. That's why the dielectric constant is equal to the reversely. So F naught by F. Okay, force. So force due to two charge particles in vacuum by force due to, so two charge particles in medium. Okay, F naught by F. F naught by F. So this is the, so dielectric constant K is equal to F naught by F. Okay, so this is about the, so three different definitions of dielectric constant. Dielectric constant, ratio of, so C by C naught, or ratio of epsilon by epsilon naught, and ratio of F naught by F. Okay, these are the three different definitions of the dielectric constant. Now coming to the dielectric polarizability. Dielectric polarizability. Okay, the ability of dielectric to allow its charge to get separated in the presence of an electric field. Okay, that means the ability of material. How much ability will be there? So how much ability of the dielectric material allow to charges get separated in the presence of electric field. If you apply the electric field, so what is the ability of dielectric material? That ability we will call it as, so polarizability. So that polarizability is so alpha. So that polarizability we can denote it as a alpha. So alpha equal mu by E. So mu is the dipole moment, average dipole moment. So average dipole moment. Okay, average dipole moment, AVG. So average dipole moment. So by electric field, applied electric field strength. So alpha is equal to, already we know that mu is the dipole moment that is proportional to the applied electric field. So dipole moment mu is proportional to the applied electric field. So there is this some constant will be there. So that constant equal to alpha. That alpha is the dielectric polarizability. Dielectric polarizability. the dielectric polarizability alpha is equal to mu by E. Mu by E. Mu is the average dipole moment. So by electric field strength. Electric field strength. So already what is the difference between P and E? I will explain you. So P means that also dipole moment, electric dipole moment. Two equal and opposite charges are separated by a certain distance. If you will take so total material, there are so many, that means each atom will act as a one dipole, because so each atom having nucleus as well as electron. If you apply the electric field, what happen? Those will be separated by a certain distance. So that means nucleus will be one side, and so electrons will be another side. That means each nucleus, each atom will act as a one dipole. Each atom will act as a one dipole. All atoms having same dipole moment. All atoms. So this dipole moment is P. Okay. So this dipole moment is yes. This dipole moment is P1. This by another dipole, another atom dipole moment is P2. Yes, someone is unmuted, so mute yourself. Someone is unmuted, mute yourself. Yeah. Now coming to the yeah. So each atom will act as a one dipole. Okay. So each atom having so some dipole momentum P1, another atom having some dipole momentum P2. So if all dipole momentums are equal, so we will take in material, so all atoms having dipole momentum, all atoms dipole momentum is equal. So at that case, average dipole momentum is equal to the dipole momentum of the atom. So all atoms having equal dipole momentum, so that's why small p is equal to, in that case small p is equal to the mu, average dipole momentum mu. Okay, small p is equal to the mu. Okay, now suppose if they are in different means we have to take average. So here dipole momentum is one atom having dipole momentum P1, another atom having dipole momentum P2. At that case, what happened? We have to take here two atoms are there, P1 plus P2 by 2, that equal to mu. That is the average dipole momentum. That is the difference between the small p and mu. Small p and mu. Okay, so if all atoms are having same dipole momentum means, so average dipole momentum mu is equal to the small p. Mu is equal to the small p. Okay, now alpha. Alpha is the polarizability. Polarizability mu is equal. So polarizability alpha equal to mu by E. Okay, so for unit electric field, dipole momentum per, another definition of polarizability is so dipole momentum per unit electric field. Dipole momentum per unit electric field is called as polarizability. Polarizability. Otherwise, one more definition is the ability of dielectric material to allow its charges to get the separation. Okay, when you apply the electric field, so that is called as polarizability. So this is the polarizability definition. Now, yeah. Electric susceptibility. So susceptibility, this polarization P bar is proportional to the uh, applied electric field. So that polarization P bar is proportional to the, so that means if you apply the more electric field, means so more atom get aligned to the so field direction, more that means charges are separated, more charge carriers are separated. That's why what happened, so this polarization also increases, that's why so P is proportional to the electric field. That polarization P is proportional to the electric field. There is a constant will be there, so that constant is chi. That constant we will call it as susceptibility. Susceptibility is chi is equal to P bar polarization by electric field. Okay, so chi. So what is the definition of chi? So polarization for unit electric field. Is called as susceptibility. So once again I am explaining here. So here if it's increasing the electric field, what happens? Polarization will be increases. That's why P is proportional to the E bar. So there is a constant will be there. So in between those two, so that constant is chi. Okay, so from this chi is equal to, you can write P bar by E bar. So that P bar means polarization by electric field intensity. So from this formula we can give the definition of susceptibility. What is the definition? Means polarization per unit electric field. polarization per unit electric field is called as susceptibility. Okay, now coming to the electric displacement. Electric displacement. So now already we said that two charge carriers, two metal plates are separated by a certain distance. Okay, so this is called as capacitor. So that means if you apply the negative field here, if you apply the positive terminal here, what happen? There is some potential difference will be there. So capacitance C is equal to Q by V. C is equal to Q by V. Okay, that is the so depends on the, so what is the charge accumulated here, so what is the applied potential, that is so that means capacitance will be depends on the so charge as well as so applied potential. Okay, C is equal to Q by V. That is in case of um, in case of capacitor. Now if you place the inside dielectric material, so we are placing dielectric material inside the capacitor. Inside the capacitor we are placing dielectric material. So at that situation what happened? So total electric field acted on this system. Total electric field acted on the system, that is called as electric displacement. So that electric displacement d bar is equal to the, so epsilon into E bar. Epsilon is the permittivity of the medium. What is the dielectric material will be there? That's permittivity of the medium. So d bar is equal to epsilon into E bar. Okay, permittivity of the medium is the electric intensity. Okay, now so displacement d bar is equal to epsilon into E bar. So therefore d bar is equal to, so epsilon naught into E bar. Epsilon naught into E bar means without applying any external, without applying any what is that dielectric material, without placing the dielectric material, what is the total electric field inside the material, that equal to epsilon, that is the, what is the polarization means due to negative charge carriers, so positive charge carriers will be there, so epsilon naught into E bar. Okay, now after applying the, so what is that, after applying the here dielectric material, after placing the dielectric material, some polarization will be occur, that is P bar. Okay, D bar is equal to epsilon naught E bar plus P bar. Epsilon naught E bar plus, so P bar. So this is the displacement, electric displacement. Okay, now coming to the, these are the some definitions of the uh, dielectric materials. So may chance to ask the these definitions also. So combinedly, so four definitions combinedly as a one question. So four definitions. So you have to write the definition as well as formula. Okay, if possible means, so draw the diagram also. So draw the diagram also for explaining that definition. Okay, so and so for each term, what is the Q, what is the A, so write that also. Okay, now these are the some definitions. So here what is that, dielectric constant definition is not given, so write that definition also in your notes. Okay, already I said that, so the definition is K equal to C by C naught, K equal to epsilon by epsilon naught. Otherwise one more definition is K equal to F naught by F. So some more definition also we can write. C is equal to, what is the formula? C is equal to Q by V. So Q by V. So from this K is equal to what we can write, Q by Q naught we can write now, Q by Q naught. Okay, like that also. So we can write so many definitions we can write for dielectric constant. Next, dielectric polarizability, and so electric susceptibility and dielectric displacement. So these are the some most important definitions in dielectric materials. Now coming to the local electric field or internal field or Lagrange field. Okay, so they will ask, so local field, internal field or Lagrange field, so they will ask anything. So like, so find out the local field, this is the important question or 14 marks question also. So find out the local field, so find out the internal field, otherwise so find out the Lagrange field. So they may ask any type. Okay, so how to find out the local field? Okay, I will explain you. 3 more minutes are there. So in that 3 more minutes, just I will give the introduction about the this local field. So local field means so after placing the dielectric material inside the capacitor plates, so so in that material what happened, so polarization will be occurs, polarization will be occurs. So due to that polarization, all negative charge particles are accumulated here, so and all positive charge particles are accumulated on the surface of the, so this dielectric material. So this is the dielectric material here, so this is the dielectric material, so these are the capacitor plates. So by using capacitor plates, what we are doing here, we will apply the, so positive terminal this side, negative terminal this side. So due to that positive terminal, what happened here, negative charge is accumulated. So due to this positive charge, so negative charge is accumulated on the surface of the, on the surface of the this dielectric material, only on the surface we are discussing here, on the surface of the this dielectric material. So similarly, so positive charge is accumulated on the this on the on another side of the, so dielectric material, another side surface of the dielectric material. Okay, now so due to the capacitor plates, due to the capacitor plates, there is a some electric field will be there, so that electric field will be E1. Okay, here positive terminal is there, this is negative terminal. So due to this potential difference, some electric field will be developed, so that electric field is E1. Okay, now so here positive charge, so here positive charge is there, here negative charge is there. So due to this, so due to this positive charge and negative charge, so there is a some another electric field will be there, that is that electric field will be E2, that electric field will be E2. And now coming to the inside the material, inside the material what happened, so many atoms are there, molecules are there, either atoms or maybe molecules will be present, so inside the material. Okay, now so if you will take one atom, if you will take one so otherwise one spherical shape, one spherical shape here, so we are taking one spherical cavity inside the material, one spherical cavity inside the material here. So this is the spherical cavity. So what happened because of the spherical cavity? Okay, so in that spherical yeah, inside that spherical cavity, so many number of atoms will be present, so many number of atoms will be present. Okay, so now here what happened on the surface of the material, on the surface of the material what happened, negative charge is accumulated. Due to that negative charge on that spherical surface, positive charge is accumulated. Similarly,